Very good. So I'm Jess. These are the names of people who are my age or younger. But of course, a lot of what I'm going to be working on is based off the work of Wojciech Zurek and Charlie Bennett here in the audience, and Adrian Kent, and of course, too many people to name. But they're older, so if you don't feel any responsibility to cite them, you know, it's only the young people that you really have to. And so yeah, so my game, the thing I'm really passionate about is wave function branches, defining them rigorously, or as rigorously as we can. And I'm going to mostly do the first half of the talk setting that up in terms of how important that is, just to make sure that you can reason about the world in a self-consistent manner. And in particular, it will have some bearing on Boltzmann brains, although this is going to be kind of off to the side. And then for the second half, depending on how much time we have, can go into the work we've been doing in terms of precise definitions. Okay, so if you're in a classical universe and you want to do anthropic reasoning, you need, first of all, you need a classical sample space, which if you then add some sort of a measure on, you get a probability space. So this is, you know, what is the set of possible things or events or otherwise that can happen? And this is something that we're pretty good at making precise, that obeys the Kolmogorov axioms. It may be a sigma algebra if you want to have you know, a continuum of possible things that can happen. And then the second thing you need is some sort of notion of observers or observations. And this is what collection of those things, the things that are in your first point, that count as observations or observers. And this is where things tend to get more vague. Bostrom is a philosopher who wrote what is probably the definitive book on the anthropic principle, which is important for, you know, Boltzmann brains. And he talks about observer moments. Don Page talks about awareness operators. And the observations then form a coarse graining on your sample space. When you add the thing to which when you add a probability distribution on it, or you add a measure, you get a probability. Sorry, and that's supposed to be, n can be made unambiguously distinct. So that you can have a sample space separate from these sets of events that form your observers or observations, right? So you have your classical state space. This is just all the microscopic things that can happen. You have your events, which are subsets on there. And you have probabilities, which are some mapping from the events to the real number line between 0 and 1. And the key feature, the thing that is almost too easy, that you don't even usually say, but the thing that makes everything work is that you have this additivity. That if you have two different of these sets, they contain none of the microscopic events, these individual i's in common, that means that the probability of the two of them is just the sum of these probabilities. Okay, and a special case of this is classical logic. It's where there is some preferred I in that set, and then all events or propositions that would normally be called, they're true if that preferred I hat is contained in that event, and false otherwise. So logic, again, just some subset of classical probability. Okay, if you're in a quantum universe, it's a little bit more complicated, right? So in a quantum universe, we can't escape from defining a classical sample space. So if we want to state anything other than just what the wave function is, if we want to say anything else besides that, we're going to end up saying this, we're going to end up describing a classical sample space, even if people aren't usually explicit about it. And I think that basically that works almost all the time, and then if you get really complicated, and especially if you're not careful with your anthropic reasoning, you can get into trouble because you're not being explicit. So the simplest case would just be if we're just going to try to describe, say, psi as some wave function of the universe, and we're going to talk about one event with a binary outcome. So then if Q is some orthogonal projector, and this is what it means to be an orthogonal projector, then we just have two different probabilities, the probability of Q or the probability of not Q, that are given as such. And this automatically forms a classical probability space. It just has two events in it. The next thing is also pretty easy. It's just where instead of just being binary, we have different options. And I'll just introduce this obvious notation here, that if I have these projectors, these are going to be the states associated with them. Where again, I'll take psi to be normalized so that these psi sub j's are not normalized. And we can take their norms to be these probabilities. And again, for different values of j, we have different events that have different probabilities to them. We get all a nice classical probability space. It's all very good. The general case, when you have iterated quantum measurements, if you're trying to describe something that's going on, either, say, if you had a description of the universe with some wave function, or if you were just saying, what am I doing when I'm working in the lab and I am making a measurement, collapsing my wave function that I've got on paper, renormalizing it and iterating this process, it just looks something like this, right? So we apply some projector, we get the conditional state. We apply the next projector, we get this kind of twice conditional state, and so on. And the probabilities for all these things are defined like such. However, this, unlike all the previous cases, is not automatically a classical probability space. And in particular, it means that if you're not careful about which of these projectors you choose and which state psi that you're working with, you can just get nonsense. You can get things that cannot be interpreted as probabilities. Okay. The necessary and sufficient condition for these to be non-pathological classical probabilities, and I'm inserting non-pathological there as sort of a weasel word, to just say that there are ways to try to avoid these conditions, and you end up getting what might be technically classical probability space, but in this very fragile way that depends on whether you have non-interacting auxiliary systems and these sort of things. So if we just want them to be reasonable, this is really the requirement that we get out, which is that these branches at the end, which I'll just call them branches without giving them too much of an interpretation right now, they just have to be orthogonal. So this is all these different events, J1 through Jm with the primes and the not primes, and they all have to be identical or otherwise the thing vanishes. And if you have this, then you have additivity of the probabilities, right? So this is just the generalized version of that key additivity thing that I said at the beginning, that if you have two different disjoint events, the probability of either of them happening add up to 1.
Question?
Yeah?
So people sometimes give you weaker conditions than that, for instance, the real part.
That's right. That's right. So this is that non-pathological weasel word that I inserted. It's all buried in there. I'm happy to argue about that, but I think nobody really likes those things. Okay. So what it ends up meaning is that when you apply all of these Q projectors, they end up playing the role of a basis, that you take your state and you end up projecting it in order to get the different probabilities onto your different outcomes that are all orthogonal. They refer to disjoint things, and we get some sort of nice classical probability space. Now, you can use other choices of projectors if you wanted to talk about different things. So, maybe normally what we want to talk about the outcome of a Stern-Gerlach experiment, but if Bob wants to talk about some sort of super weird projector which may or may not be realized in an intuitive way as a quantum measurement, he can certainly calculate probabilities, right? He can certainly take an arbitrary wave function, or perhaps the wave function in the universe, stick in his projector, calculate a probability. He can stick in lots of projectors as long as he obeys this condition that I was talking about, and he will get a working classical probability space. Now, whether you want to talk about that one as being useful or not, maybe it is, maybe it's not, but the point is that it at least obeys the Kolmogorov axioms. However, it is key that if you pick one of these spaces, if you say, I'm going to talk about the probability that we got spin up, and I also want to talk about the probability that the moon was in a certain location yesterday, I can only do this sort of reasoning and pretend like these are real facts. I can only talk about them as if they're real things, so long as I pick one sample space and stick with it. Okay? If I combine two different sample spaces, if I start saying that I'm going to take a probability that I got from computing with respect to one sample space and a probability that I got computed with respect to another sample space, and start trying to put those things together, combine them with and or in these sorts of logical operators, you get nonsense. So the obvious example is that you can't pretend that the electron passed through a particular slit in a double slit experiment. After all, you can, if you want to calculate, you've got some sort of, it takes two different paths. It's got some wave function associated with this. I can stick in the projector that corresponds to the electron going through here and here, and that will give me some number. That number is calculable. But if I also calculate the chance that the electron ends up at a certain part of the screen, then this probability plus this probability does not equal that probability. And this is when we start, this is why you can't say things, you can't assign whether there is a fact of the matter about which slit the electron went through. Less obvious examples are such as the one that Renata is going to tell us, I guess, tomorrow? Yeah. That if you start thinking about observers, you start putting observers here, putting them in superpositions and starting to say, the electron is going to start making conclusions about things in the outside world. Do all of those statements line up? And in particular with this example, it's going to be seen that it's not just a matter of statements that are probabilistic, but you can do it with statements that can be made with certainty. You start getting contradictions. Yeah.
So when you say these, you cannot add the probabilities, you mean in the classical probabilistic way, right? So still the image I have in my mind with the path integral, for example, that I find the probabilities for every point and then I make them interfere. This is not classical way of adding probabilities, but this is a valid way still, right?
Well, you're adding amplitudes rather than probabilities.
So you're talking about adding probabilities now only, right?
That's right.
Not amplitudes. Okay, because I got a bit confused.
That's right. So you can certainly add probabilities, and that is in fact how we do the calculation. Yeah. What's wrong?
Well, I'm just trying to parse this out, but I think so far what you're saying in my limited translation is if you do quantum mechanics wrong, you get crazy answers. Yeah,
so if you had a wave function describing this experiment, you're treating it unitarily, there is nothing in the math that tells you that sticking the projector here is more important than sticking the projector here. There's something sort of intuitive we have. We say, well, the thing we care about is the measurement outcome.
You shouldn't add together.
Good, good.
Missing dollar.
That's right. There are certain things you shouldn't add together, and in some sense you can think about my project as figuring out what are the preferred things that we were interested in, what are the ones that we're not. So another way to say it is that, so one of these corresponds to things like the moon is in a certain place tomorrow, and this is the outcome of the Stern-Gerlach experiment. Whereas this one is going to correspond to some projector that is pulled out at random from the space of operators on the Hilbert space of the universe. And I can calculate it, I can calculate consistent probabilities with it, but it doesn't correspond to anything useful that we can match up and agree on. Okay? So we're trying to figure out, ultimately figure out what distinguishes this from the other things.
Sounds very familiar in the consistent histories.
This is all consistent histories. Is there anything new here?
You want to call out, say, oh, don't just assume it's the same old stuff.
Right.
Right. You're going to go somewhere different.
Right.
So far.
So far, I think it is very similar. You can think about this as just a restatement of You can reason with respect to a given set of consistent histories, but if you don't pick a particular set, there's just multiple sets, they're all sort of on equal footing, and if you try to combine them together, you get nonsense. And the statement is just going to be that when you do this sort of stuff with Boltzmann brains, as people often